Hey there, I'm Rachel Eisgruber here with Michelle Wong, Ryan Coffin, Hadi Rabadi, Joshua Raber, and Justin Henix. We are Team 1. Our advisors are Professor Aaron Nelson and Professor Jared Nelson, and our project is the open source 3D powder printer. Just a little overview of our project before we get started. This printer is a binder jetting style printer. Binder jetting is the method in which a binder is laid down on a powder base layer by layer to form a 3D object. Think of it if you were to print out each layer on a standard paper printer, cut it out, and glue it all together. The binder is the glue, and the powder is the paper.
The advantage of using the binder jetting printing process as opposed to fused filament fabrication, which is offered to all students on campus, is that binder jetting allows for intricate geometries to be created without the extra support material. The powder surrounding the part acts as the support material, which will be carefully removed in the post-processing chamber. Overall, we have improved our version of the printer by increasing the overall build volume of a print, improving the printed circuit board layout, as well as updating the user interface of the Oasis source code.
This printer has been designed to operate with the use of Inkjet Technology, a method that utilizes Hewitt & Packard 45 ink cartridges to apply a binder liquid to the powder. These cartridges can be filled and then reused with any liquid binder. The HP45 cartridges hold 300 nozzles that can apply the binder to the powder in 600 dots per inch. With a high DPI, this printer can print objects that will be, for most printers, too complex in geometry.
A heat transfer finite element analysis simulation was completed on the motor that controls the pistons. These motors control the Z motion of the feed chamber and the build chamber. While in operation, the motors generate a small amount of heat. These motors are mounted into a 3D printed ABS piston. With this heat generation, the ABS would be hot to the touch. Using an ANSYS simulation, the heat distribution from the motor was found to be minimal. The addition of a heat sink showed the same temperature distributions and the same maximum temperature. Therefore, the piston's contact with the motor was reduced to allow more passive cooling to the motor.
The finite element analysis completed primarily focused on the deflection of the aluminum extrusion when the gantry, approximated to be 18 newtons, is acting on it. The gantry consists of the spreader motor, the print head, 3D printed components, and a 30x60 aluminum extrusion. The completed analysis done on ANSYS shows that the frame will deflect at the center by 100th of a millimeter. This is very insignificant and did not pose any issues with the movement of the gantry overall.
With the aid in electrical datasheets, schematics, and layouts, it was found that most of the information needed was not documented. Knowing this, we created the documentation before any changes to the original design were made. A redesign was completed on all printed circuit boards, electrical layouts, and controller hardware needed for operation. In addition, the memory storage buffer for the inkjet was updated. A faster embedded processing board from the computer controller board to the computer was added, and all electrical hardware was updated so that it no longer used obsolete electronics.
Since this printer originates from the open source community, the code was primarily written in two languages. C++ was used for the firmware, while on the other hand, Python was used for the software. Files that were taken from the open source community were not necessarily completed. The firmware files had to be adjusted such that the metrics and measurements could be more compatible with our physical build. For instance, hard-coded dimensions had to be changed so that the gantry does not run past the limits of the build. Functions and methods in the software had to be fixed or completed as testing proved to be inconsistent at times.
Printed items taken out of the printer require post-processing as they are very brittle and covered in excess powder. Cleaning off the excess powder can be a very messy and hazardous process, so a post-processing chamber was constructed to contain the entire process. Printed parts are placed into the chamber where they are cleaned with pressurized air and then treated chemically to solidify the bonds of the binder powder. The chemical treatment involves coating the part in a hardening adhesive such as superglue.
We would like to give a special thanks to our advisors in the HVMC for their generosity. This concludes our presentation. Thank you for watching, and have a great day.